Good morning, everybody. Ready for the week?
No.
Yeah. No? Hey, I like the honest answer. Bonnie, did you have somebody ready for the prayer? Okay, well, you just keep going. Some of the fun stuff I did this weekend, my son had a hockey tournament down in Las Vegas. We played a Lutheran school, and anyway, lots of fun down there. On the way back, went to, pardon? Well, we played the same team 3 times in a row over the course of 2 days, and we lost twice, but then we beat them the last time, which is the direction we want to go in. So hopefully that means we're learning something. Either that or they got tired of beating us and let off. Either one. Just kind of like on a softer note, I got to go to, I just randomly dropped into some ward in St. George on the way back, and I liked this older guy who was giving a talk. He got a PhD in one of the hard sciences, and he talked about how over the course of his life before his mission, I think he might have been the first person in his family to go on a mission. Before his mission, the highest grade he got in college was a C-, and then after he got back from his mission, the next best grade he ever got in his next level of college was a B. And then later on, he went and got a PhD at one of the best schools in the country, and he got straight A's the whole time he was there. And he just talked about how in his journey that it was all the Lord's hand, and he just testified that the Lord can do more with you than you can do with yourself. And I just wanted to support his words, reinforce those words. I believe that we can all be a lot better than we can be on ourselves by ourselves with the Lord's help. So anyway, that was cool and meaningful for me. Bonnie, did you have a prayer person for us?
Yeah, so today is Will Graham, who does not have a favorite apostle, and his favorite Kettles persona is Tony Hawk Kettles.
Whoa, Tony what? Tony Hawk Kettles? Oh, yeah.
Our dear Father in heaven, we're so grateful for this beautiful day that was given. We're so grateful for the chance we had to hear of you, IU, and be studying. And grateful for the many things that we've learned, and grateful for our professors and for the time and effort that they put into preparing class each day and making this a great learning environment for each of us. We ask you to bless us so we can be able to retain the information that we're learning and be able to apply in our different jobs and internships that we might participate in. And we ask thee to bless us with thy spirit, and we say these things in the name of Jesus Christ.
Amen. Thank you. How about you guys? Anything you'd like to share from your weekends? Anything good? Wait, what's? Okay. I saw that there was like a 1-point win over Houston. Is that right? But I don't know any other details about the game.
It was a buzzer beater.
It was buzzer beater. Oh, okay. Coronavirus is still bad. Okay. Any other thoughts or experiences? Yeah, Bryce.
Team USA won the freestyle ski dual mogul at your rally this weekend. Go USA.
Awesome. USA. Like that. America. All right. Any other things to share? No new engagements or something like that? Okay. Well, let us. Do you have any questions about class stuff? Class stuff. IS 404 related material. Okay, so the plan for today is to Grant.
Do we have to, twofold question, for the tests and everything, do you want us to remember and memorize like the whole masking thing? And like how to mask, how to get the Subnet Mask?
The answer is yes, and we'll have 2 days to go over that, and then I'll give you a worksheet, and I plan to be hard but fair, that the stuff that you do on the worksheet, I hopefully won't go outside of the scope of that, so you should be okay after we do things a few times. And then if you're still confused, you can talk to, by the time we get all the way through this, you know, you can talk to me, you can talk to TAs as much as you want. If you picked it all up from the reading, you're a better man than me. So that's some tough sledding, I would think. I think that's the toughest material I think that we go through in here. Today we'll go through a little bit of routing related material, and then we'll start on the subnetting, and we'll have at least 2 days on subnetting stuff. And I'm going to try to be real careful, as if it were a landmine field as we go through that. Just try and make sure we get it real well. Okay, yes?
On the schedule, it says the test is on the 26th. Is that gonna be like in class, or is that gonna be like?
I know we took a vote, but I think that the best way to do this is we're going to do it in class, and that we will have an online portion and probably a handwritten portion. Oftentimes, there's some diagrams and stuff I like you to draw. And so having a paper-based portion will also allow me to see your diagrams. Okay, with the routing activity that we did last time, it ended up being a little bit cut short compared to what I would have preferred. But what I hope you would have pulled out of that is this idea that it is a little bit tricky to figure out what even though you can talk to your neighboring routers, it is a little bit difficult to put together the route tables or the route graphs. A little bit chaotic, and in a way it's just kind of fun to do that. Also to be aware of the fact that it is possible for messages to get communicated as they go through, they can get messed up with noise as they go through the network. So it's just some fun high-level ideas related to that. We're going to talk more about routing right now, some of the mechanics of it. So routing, how you get from one place to another across a network. So, for example, in the next slide, we have computers A2 and C1. The question of routing is, how does a packet go from one place to another? How does a router make that decision where to send it? So here's A2, here's C1. We're going to come back to this slide in a little bit. We'll get to the details later on, but right now all we're concerned about is these yellow computers. So how does a message get from A2 to C1? That question is meaningful because as we leave our local area network with a switch, we hit a router, and we can either go from this router to that router, down to that LAN, or we can go from this router to that router, back over that router, and back down. That's really the high-level idea with routing, that there are multiple paths that you can take, and a router needs to make a decision such that your packet can get there reliably and quickly. So there's a picture of a router. We've seen those before. I brought one to class. We're trying to connect independent networks. And I'd like to introduce a different analogy today. When we talk about networks, we might also talk about them in terms of real-world analogies, such as street names versus the houses on a street. So when we talk about a network neighborhood, we might talk about that in terms of, like I'm going to make a comparison here. Over here on the east side of Provo, there's the tree streets. So we might say that, look, these aren't the real names of them, but there's like Maple Street and there's Apple Street and stuff like that. So you might think about your network neighborhoods like that. There's Apple Street and Maple Street, and then the IP addresses themselves, so that's kind of like your network. And then the IP addresses themselves are like the individual houses in that neighborhood. So routing really primarily helps us get from neighborhood to neighborhood. As a packet comes into one particular switch, or sorry, not switch, but router, it's like, okay, I know I'm connected over here to the Maple Street and over here to the Apple Street, and then as that thing comes in, a packet comes in, it can send it out to a particular street, and then with the help of the switch, it'll make it to its correct host. Blah, blah, blah. I like this table that was in the book, in the textbook. So here is a list of the exact same network or the exact same neighborhood if we're talking about like Apple Street or Maple Street. It's just saying there's a lot of different individual entries in this table. All of them lead to the exact same neighborhood. And really, the way this is written, 16 means that really we're just talking up to this second dot. So when a router receives a packet that's destined for anything within 131.247, anything that's after that number, it doesn't need to look any further than, because this is, the way that it's written there, it's like saying Apple Street or Tree Street or something like that. But, so it's got a lot of options in this table. It says I could send it to here, I could send it to here, I could send it to here, I could send it to here. Of course, it has to make a decision. You know, what's the route that's going to be the fastest? What's the route that's going to be the most reliable? Yeah.
So when you're going up to the second dot, is that just searching for the other routers? I didn't quite get that.
Okay, so in practice, so this is going to become clearer in just a few minutes. But in practice, I'll give you an example. Let's just say we have 131.247.0.0.1 is where a packet is destined for. As it comes into the router itself, because of this thing that says /16, it says I really don't care what happens after the 247. That I only look at it at the street level name. I don't look at routing in terms of the individual stuff. And it has to do with the way the 16 is written. The 16 says don't look at anything after this. So even though the packet is destined for something that's in those two numbers, the way this is written says, hey, if I get a packet that starts with those 6 numbers, I'm not going to read any further, and I'm going to send it to one of these. And so that'll become clearer in just a couple of minutes. So it's got lots of options. Usually when we have something like a metric, this is some number that's created related to our routing protocol that makes some of our paths more preferable than others. We'll talk about that in just a second. So we just saw an example of a routing table. Here would be an example of how you would create an entry in a routing table. And perhaps because I'm a computer programmer at heart, this appeals to me a little bit. So if I'm at the command line, I can type in IP route and then these next 3 options, and then I can create an entry in my routing table similar to the one we just saw a couple slides back. So here would be a command. If we were logged on to our router, we could type IP route. So what we're saying in this one is, if I want to get to some IP address that starts with 10.10.10, this number right here tells me, and we'll do more about subnet masks in a minute, so just trust me on this one for now. This number right here is telling me anything that comes after the 10, I'm not going to worry about just yet. The way this is written is saying anything that comes after 10.10.10, I am accountable for. To get to anything within 10.10.10, so basically from 0 to 255, I'm going to send it to this number to this IP address right here, 10.10.200.2. So, for example, if something 10.10.10.1 came in, I'm going to send it over to this network right here. So that's the programming command we use to put it in there. So this is just for illustrative purposes. If you decided to make this a career and you wanted to enter this stuff in by hand, this is eminently doable. Yes?
I don't know if I caught that. Were you saying the first 2 IP ranges are ranges?
This is a subnet mask. This is the network neighborhood right here. So this is saying Tree Street.
And then what's the second one?
This is a subnet mask, and this tells us like what to read with the number within the number that just preceded it.
Okay.
We'll cover those in just a minute, so you can kind of ignore it for the moment. And the last one is saying, hey, if you want to go to the Tree Street 10.10.10 and anything comes after it, send it to this IP address. And so we can create a whole bunch of entries like this programmatically. And then after you've done that command and you use this command, show IP route, this will show you the routing table on your, this is output from a Cisco router. This will show you the output of all the routes that are in there. And so this one, it gives you a little lookup table of information, and then it actually tells you the key information that you care about. So down here it says, if you want to get to 10.10.10 and anything that comes after that, send it to 10.10.200.2. And then it says, right after that, I am physically connected through a port right now to the neighborhood 10.10.200.0. so this presumes that if you want to get to this address, that if we send it out through that physical port on your router, that it's going to make it there. So, as part of this class, I'm not planning to teach you how to program routing tables or view your routing tables, but just as an illustration, hey, that's not so bad. I think if I did this a couple times, I could understand how to do the command to create a route and to view the routes and then interpret them. Yeah, Spencer.
Do many people actually manually do this?
Do people manually do this? Man, what a prompt. Okay, that's the title of the slide two slides from now. So I'll get there in just a second. So before we get there, so good, he's inspired. All right. So before we get there, another thing that a router takes into account as it determines which of the multiple paths it has available to it, it can look at any of these metrics. So it can keep track. It can look at those metrics and decide, hey, among those choices, I'm going to look at hop count, reliability, the bandwidth, the delay, the load. There's all kinds of metrics that are out there that can be used for it to make its decision. So just so you know, at a high level, this isn't. I'll tell you what I want you to know and memorize. This part generally is just for your general knowledge. Okay, so to Spencer's question, do we want to do this manually for our whole network? What do you think?
No.
No. So you can, but you don't want to. Because it's going to be error prone and it's going to be time consuming and tedious. And so it can be done autonomously. We have two different categories of connections or routing contexts. So our first context for where we're going to have this done autonomously is when we're working internally. And when I say working internally, what I'm talking about is more than just how do we program a single router, but how do all the routers within a particular region share information with one another? The rules for that, for within a network that you control, like on a group of LANs, we would call that interior gateway protocols. So, and then there's another set of protocols, exterior gateway protocols, which are more for between routers on the public internet as opposed to related to local business parks. So here is something that I would like you to learn, just to be familiar. So in the same way that, if we were going over the Star Wars movies, I might like you to know, a list of the bad guys and a list of maybe our most common Jedis. So our Dark Lords of the Sith, and then our Jedis. And so we might do like Obi-Wan versus Darth Vader, Darth Maul versus Luke Skywalker. So same kind of idea here. Just know some of the key names here. So for our local area networks and the routing that we're going to use there, not on the public internet, we're going to use OSPF, RIP, and EIGRP. Open Shortest Path First, Routing Information Protocol. And then the exterior gateway protocols, EGP and PGP, BGP. So one of the certifications I got recently, I got a couple related to Amazon, and I see BGP come up a lot. The idea that you're trying to connect your local corporate data center and its networking to AWS and its infrastructure, and you're sharing data back and forth. And so the configuration you're doing in there, since you're going across the public internet, ends up being BGP. So anyway, just so those things I do want you to remember at a high level. The other stuff, just a general idea. Oh, there's tables of information. It helps us get to the right neighborhood. Blah, blah, blah. Okay. Here's the last thing related to routing that I wanted to go over. So there's a lot of detail on here, but as I look at it, I find that this is a really good teaching exhibit. So, and I don't know that I'll go over every single bit of it in detail. I might just ask you to go back later on and look at it a little bit. So before, I was talking about the fact that, hey, routing is about determining which path we send our packets down, which router we send our packet to, starting at one router if we started today and had to get to computer C1. But let's look at some additional pieces of information here. One of them is that we have, in this diagram, we have 4 different LANs. And each of the LANs has IP addresses associated with it, and they all have different IP address schemes. Because they're in different IP address ranges, sort of like, again, your Tree Street, your Maple Street, etc., anyway, their addresses are going to be different. So, for example, A1 and A2 has 10.10.20.1, and this is the network neighborhood that they're in. So 10.10.20, if we just stopped there, that's the neighborhood they're in. That's their network. That's like saying Tree Street or Maple Street. If I go over here to, let's maybe LAN D will be easier to see. LAN D says its neighborhood is 10.10.5. That's its network. So, and then so as I look down here to the computers attached to it, I see 10.10.5.1. So the 0, by convention, historically means this is my network, so it's not any particular place within the network, it's just the general network. And then the hosts within that network, the particular devices, typically get numbers that increment starting at 1, 1, 2, 3, 4, etc. So we literally have kind of 4 networks that are represented here, 4 different neighborhoods. Each of them are represented by a network that starts with the 0. So that's kind of cool. Another thing that's interesting about this is, so as we go off of any particular router, that every single router is not is at least this upper part is not connected to a particular IP address that you're seeing. It's connected to a network, a neighborhood. Every single one of these is connected to a neighborhood. But then there's, so that's something to know and to think about. As you think about the previous routing table that we saw, it was all a list of network neighborhoods, not particular IP address destination. It was all a list of neighborhoods. And so again, from the perspective of a router, it's looking for networks that typically end in a 0. Those are the neighborhoods or the street names that it's being sent to. But here's another little twist to add to this now. Oftentimes when we're looking at networking devices, we see this funny little notation there, like FA0/0, FA0/1, FA0/2. Typically what that means is fast, like something like fast Ethernet or gigabit Ethernet, and then the very last digit represents the number of the physical port on the back of it. So plugged into port labeled 0, well anyway, so there's going to be a port labeled 0, a port labeled 1, and a port labeled 2. And as I come down to here then, so I'm going to look at my router A. So attached to, let's see, fast Ethernet 01, so 01. This interface right here has the IP address 200.1, so it has a real address associated with it. This, let's see, let's go to number 2. So this interface right here, it's on this network, but it has, this interface right here has an IP address associated with it. So the network it's attached to is called 100.0, but the interface on here is 100.1. And in order to participate in a network, you have to have IP addresses within that network. And so let's see what it's connected to. We go over here to router C. Router C on connection 02 also has, wait a second. That's broken. That's messed up. Oh, sorry. Well, is that mislabeled?
Yeah.
Okay, so so what we're supposed to be seeing here, what I was looking for, is on this connection FA02, there's 10.10.100.2. So there's a .2 IP address over here, a .1 IP address over here, and then .0 is the name of the network itself. And so so anyway, does that, hopefully that makes sense. You're thinking about any 2 devices like routers sitting on opposite ends of a network. There's this generic name, and then each router has an IP address that actually sits in that network. Yes?
Okay, so if I'm
Mm-hmm.
Like, the computer will send the full IP address,
Yes.
but the route, when you're like mapping and that kind of stuff, the routers will look at only those first few numbers.
The router's only gonna look at the first few numbers, because it doesn't wanna have table entries for every single IP address in the conceivable universe. And so it just gets general neighborhoods, like, oh, through this, if I've got 4 ports, I know that stuff in this beginning range, I'm gonna send through that, this beginning range, I'm gonna send through that, and then a couple entries like that, yep.
Is this how we know by IP address, like physical location? Because you can like Google an IP address and it'll say like it's from this part of the world. Is that because we have it all mapped out, like these routers belong in this part of the world?
Well, this certainly doesn't hurt, but I think that there's another reason why we'd know that, and that is through the Aaron Corporation, that we assign out IP addresses to countries and
Okay.
blocks. And so it's like, yeah, the Iranian internet service provider equivalent of Google or Cox, like we know that they have this range. And so that's,
Okay.
that's probably first and foremost the reason why we know where traffic is coming from, because they got assigned an IP address, range blocks. Okay, so this is, this totally geeks me out, but I fear that if I'm just explaining it in front of everybody that it might not all sink in. Like, but I super like just like sitting here and just like looking up all the numbers, seeing how everything fits together. This, I think, teaches you a lot, if you just sit in silence and just think about it for a little while, teaches you a lot about how networking works and routing. So, good thing to just look over and study later. All right, yes?
Just one more question. The chapter in chapter 9 talked about subnets.
Yes, we're going on to subnets now.
Okay. Okay. If you're gonna talk about them.
Yep.
So
Okay.
this is not subnetting.
No, we're not talking about subnetting directly yet.
Yeah.
All right. So I will post this at the end of the day today. Go back and just kind of study the numbers related to this slide that Gary would love. There's a couple pieces of optional information there, but I don't think it's going to be critical to you at this point in your life. If you go and get a certification, you'll need to know some of that other stuff, but we're good. All right. Woo. Not this one. So, all right, just for giggles here, I've got 104 slides so far. I went through this. I created this lecture material 3 different times over the weekend. That's how much anxiety I have over it. It's hard to explain. But I'm not actually going to use all of them. Most of that is just the stuff that the first and the second round, I just kept on pushing it farther and farther down the list. So we'll probably never, we've got a couple days to go through this. Okay, people want to know what are the things that I'm supposed to take out of this. And of course, I do put on the content portion of our website, what are the study areas for every area. Really, I'm only suggesting 2 things related to routing. But as we get to subnetting, I want to be upfront with here are some of the things that you'll find in that study guide. But right at the start of this, what are the things that you should know? So, word for word, I would like it if you could take an IP address such as that one, along with its subnet mask, and tell me everything there is to know about the IP address and its network. Sounds simple enough. And ironically, after you learn this stuff, 9 times out of 10, I can just glance at something and within about 1 second, maybe 2 seconds, I know all of those answers. And yet, sadly, as you learn it the first time, it might take many hours to get to that point. So, you'll know what I mean once you get to the other side of this knowledge base. Yes? We're going to go through in great detail what we mean by this. So, I mean, what does it mean to know everything there is to know? Well, we'll go through examples of that in just a little while, over the next couple days. Another thing I would like you to be able to do is that if you were assigned something that looked like this is a network address block. What this is saying, and it just jumps off the page to you, you have been given 16 bits that are assigned and 16 bits that are variable. I'll explain why you know that in a little bit. I want you to be able to design, given something like this, in this notation, I want you to be able to design a solution for organizations based on an address being given to you in that format. So those two things are actually really simple after the fact, but I think conceptually it's hard to go through. In fact, even as I've watched different instructors on YouTube talk about this, they even talk about how they have people who are professionals that go around and lecture on subnetting all the time. They say they have to review all the time. As I look back at my student experience, I should probably stop talking. This is like the one thing I forgot. I'm like, oh, I don't remember how to do subnetting. I remember that was like the harder part. So if I were to draw like a little graph of maybe your enthusiasm or ease of pathway going through the class, this is it. This is, or maybe I'll do it the other way. This is the hike to Mordor. Then we'll come back down. So we've got 2 days of hiking. We've got 2 days of hiking to Mordor. It is what it is. Eye of Sauron all over you. Okay. But I will go as slow as we need to go. I will go as slow as we need to. And you also have the TAs and myself. I'll help you outside of class as much as you want. So we'll start off having a little fun, and then we'll go into the mist of darkness a little bit. Okay, before we get into the mist of darkness, let's kind of warm up a little bit with some fun. So here's something I would call useful. Helps us learn, but it's not directly on the test. So your home, as it relates to any of the routers that you get, like your Google Fiber router or whatever gets assigned to you by Cox, it's an autonomous network in the sense that, they gave you a block of 256 IP addresses, and they just kind of magically assign themselves out to your computer. So it's kind of an autonomous network in that sense. But do you have to let them be in control? No. You can be in control. You can manually assign those IP addresses out. So here's a way that you might manually assign things out. As you get more and more Raspberry Pis, and your children get older, and you have lots and lots of Legos sitting around, both of which are true for me right now. I've got big old boxes full of Legos. You could make yourself an array of Raspberry Pi devices and set them up this way. And you could organize it. Rather than just having them get automatically assigned some IP address, you could assign them the numbers 2 through 26. Isn't that nice and tidy? Yes, it is. For those of us that are control freaks, we're like, oh yeah, that feels comfy and nice. And if also at our house, we also have a bunch of individual devices like computers, we might be like, oh, hey, that's like 2 through 26. I'm going to give these 30 through 45 because I'm super organized. And so when all is said and done, you could at your house, given your 255 addresses that are assigned to you, you could put things in blocks and categories like, hey, 2 through 26 is going to be my Raspberry Pi server farm. 27 to 42 is going to be personal computers. Televisions is going to be 42 through 50. And maybe any smart devices like your thermostats and stuff like that, I'm going to keep them in a neat, organized block too. I'm going to give them 50 to 100. Yeah?
Aren't some of those automatically assigned already when the computer boots up for the first time?
What happens is it reaches out to your devices, and then it gets assigned an address. It says all of your devices, when they come online, they reach out to the local area network. They said, can you give me an IP address? And they get assigned one automatically. But you can purposely and manually assign a different address that's within the scheme that you want.
Retroactively.
Mm-hmm. Yep.
Okay, so one thing I'm a little lost on, do all your devices like within your home then, are they local IP addresses and your router is the only one that's a public IP?
Your router is sitting on 2 networks. It has your home device it sets up your local area network, typically with the IP address scheme that you see right there, and so it'll assign those all out. But it also sits on the public network itself, just like a regular router. So it's got a public IP address, and that's how it connects to the rest of the world.
Yeah.
and then it's got, on the other side, it's got a local area non-routable address scheme.
Okay.
And you can mess with both of those. So I typed in like organized or something like that, and so if this is how you do the rest of your house because you're type A, then maybe this works for you. Okay, so would you like to see, just like at a glance for fun, like how you might do this on your local home device? Okay.
Yes.
It's going to be different in every device that's out there. I'm using Google Fiber, and so I'll show you how, but I've used lots of different devices. The important thing about classes like this is that you get the big level ideas, because all the interfaces are different for every different device you use, but the concepts stay the same. If you know, hey, I need to administer a local area network, or I need to fix my public IP address, all that stuff, knowing that high level knowledge allows you to do it in completely different interfaces. So I go to Google Fiber, I just go fiber.google.com, and here's my house. Welcome to my house. So,
The promised land.
yeah. It's the promised land. So you can see here a list of the devices. This is like so here's all the Wi-Fi connected devices, and you can see what's currently connected in green. So we've got iMacs and iPhones and Raspberry Pis and televisions and laptops and all sorts of things. Up here are the physically connected devices. I have one physical connection that's going to my Raspberry Pi. I have another physical connection that's going to an IP-based phone. So both of those are just physically connected. And so let's see. So if I click on my Raspberry Pi that's got a physical Ethernet connection on the back of it. Okay, it's got a name. The name is changeable, but this MAC address is not changeable. So how does it get all these names? Well, again, it creates a table inside. The MAC address is permanent to every device on the network, but the names we give it can change. We can see that currently this Raspberry Pi device has been given, automatically assigned this address, 192.168.1.248. And here's where the magic would happen. If I open this up, it says reserved IP. So I could change, if I wanted to, I could change this address. So I said if I wanted to put things in given ranges, I could just change it right here. As long as it's not assigned out to another address right now, I could change this right here and then keep everything nice and tidy in this way. So I could go through every single one of my devices and I could organize things in that way. Just as a side note, I have it so that I can SSH from anywhere in the world over to my my Raspberry Pi. I can just do SSH and then my home IP address. And what I did to do that is I clicked on this little add thing right here, and this is doing port forwarding. If I go back up to the promised land, which is the name of my overall network, and if I open that up, this right here is my public IP address. So technically, if you were to ping this right now, if it were to respond, that's its public address on the whole internet. That's how all of my internal devices are getting. Once every single one of my internal devices hit the router and they go out to the public internet, this is how the public internet sees everything that's on the inside of my router. It recognizes them with this address. Also, remember how we talked about private address schemes? Right here it says what's the internal address going to be. These three things are all related to my internal LAN. The network address schemes that are private that start with 192.168 or 172.16 or 10.0, any of those three can be entered into these and are usable as part of my local area network. So if I don't like the default of the 192, I can use the 10s or the 172s. When you spin up stuff in AWS, you will have the same options out there in the cloud. You will be setting up all kinds of different servers. They're going to have a public IP address, but on their internal network, you're going to be able to determine what the LAN addresses are going to be for your local addresses, for your secret addresses. So, okay. Yes, Pete.
Would you change addresses just to keep things organized, or is there many bigger purpose to changing?
Well, there are a few different purposes, and I've got some slides. There's like 3 options, 3 reasons, main reasons, and I'll go over that in just a little bit. Okay, does anybody need any type of break for a minute? You want to like 30 seconds? Okay, just like breathe, talk to one another, because this was the easy part. We're about to hit the hard part. Okay. Yes.
Yeah, so one day, like, things seemed to be going okay. We were sitting at the volleyball game, and then I was like, "You have Snapchat?" Yeah, I have some Snapchat. Yeah, call me Snapchat. We were like following each other, and basically, after that, I decided I wasn't interested, and I tried to set up with my roommate. She's like, "I want to go up to do this." And then after a while, I stopped playing. I checked Instagram, she's gone. Snapchat is gone. It's like, this is good. Check that off my bucket list. Officially deleted all the great that. Yeah, it's great. I didn't like it. Oh my gosh.
Okay. All right. Let us move forward. We have come to the foot of the volcano. Let us walk up the volcano now. As we go along this journey, feel free to tell me every 20 minutes or something, hey, I could use a break, or ask me as many questions as you need, etc. Okay, subnetting. Kind of the theme here is that you can subdivide your network into different parts. Assuming that you were given a block, you can subdivide it. So that's kind of our part 1 idea. If we have an address that looks like this one, technically we can conceive of it as having a network portion and a host portion. So the network portion would be like, hey, there's some part of this is the tree street, like Maple Street, and some part of this is the IP address associated with a particular device. We don't know in and of itself where the dividing line happens. We need some additional information that comes from subnetting. But know that contained in here is a network address and a host address, a neighborhood address and a particular street house number. Yeah?
Is that like how we can look up like the first digits of the IP address and tell where it's coming from? Is that the same like host portion that we're talking about?
Do we know where it's coming from by looking at the first parts of it?
Online you can like look up part of the IP address and it'll tell you what the network is.
We know what the network is based on the subnet mask. So the subnet mask is another number that looks like an IP address, and that number will tell us exactly what the network neighborhood is. And we're going to go through examples of this. So before we get to our subnet mask, this is how it comes out. If we look at our network, our IP address in terms of bits, somewhere there's some arbitrary divider which is revealed by our subnet mask, but somewhere there's some arbitrary divider on the bits, and wherever that stops, whatever is to the left of it is the network address, the neighborhood, the tree street, and whatever's to the right of that defines the host address, the address of the individual unique identifier of a house or a device within your network. That's at the high level. We can expand our idea of the network, because so oftentimes we get assigned a block of addresses, like you get the 256 addresses at 192.168.1. something, and the rest is yours. What we can do is we can actually subdivide whatever is put into our control, and we can actually make some of those bits part of the network address. We call that, again, subnetting. And for practical purposes, we might just call that the network. It's still the network address. So for right now, just assume that when we subdivide our network, we just expand the definition of our network, and then again, everything after that is the host IP address. Okay, stepping on through some stuff. So visually, here's a piece of graph paper. Some of you are being taken back to high school right now. Imagine this maybe is a representation of a block of IP addresses that you have been given to manage. And it's within the range 192.168.1.0 all the way through 255. Alternatively, this exact same range assignment could be represented this way with Cider Notation. I will talk more about Cider Notation later, but this is actually equivalent, both of those. So when would you get assigned a block of addresses to subdivide, to administer? Well, one context is if you were given local area networks to administer. So if you were working in, kind of on the physical side of things in IT, given a room in a building, or maybe several rooms, you might take your block of IP addresses and allocate it to different floors of cubicles, or even subdivide your cubicles and say, this is one side is accounting and the other side is developers. So that's one way that you might do it. And historically, through many decades of this program in IS, that would be a realistic application of your skills from this class. However, what's probably like 10 times more likely these days is you're going to be working with AWS, and you're going to be taking your block of IP addresses. We call this the VPC, the Virtual Private Cloud, and then we subdivide our IP addresses into different groups. We'll allocate some of our IP addresses for something like our databases, and some of our IP addresses for something like our web servers. Okay, on to the Cider Notation.